Okay, in this video we're going to walk through the idea of demodulation by simply downsampling. Okay, so this goes back to your AM/DSB express carrier simulation that you did in Matlab. You're going to modify this, and I'm going to talk about the ways in which you modify this. It turns out we're just going to have a few lines of code. You need to make a change to your original simulation, most likely in terms of the sampling rate, but then you just add a few lines of code and you can show that you can demodulate AM/DSB express carrier by simply downsampling. Okay? Alright, so remember we started with an analog signal, and here's the picture of that. Alright, this is our analog signal. It's got a maximum bandwidth of 4K. And what we did from there is we modulated that, so we sent the signal up and back by 20 kilohertz using an oscillator, a 20 kilohertz oscillator. And in order to make this happen, we did it all in Matlab. We had to resample so that we'd have enough headroom in the digital frequency domain to make this happen. So it turned out we used the Matlab Resample function. Last time, I gave you another video about how that particular function worked, and it had this block diagram that has an upsample stage, a low-pass filter stage, and a downsample stage. Okay, so when we did our original simulation, we had to upsample, and we had a minimum upsampling requirement. We had to do twice the highest frequency of the modulated signal, and so I go back up here and I look. The highest frequency was 24K, so 20K is the center frequency that we modulated to, plus the 4K gives me the 24K times 2 is 48K. So we know we had to resample the speech file before we did the modulation step, so that when we modulated, we'd have enough headroom to move that up into the spectrum up to 20K. Alright, so you had several choices that would have worked. I didn't specify which upsample factor to use. If you did m equals 1 and l equals 6, you would get 48K. If you do m equals 1, L equals 7, 56K, and so forth and so on, all the way up to 80K if you used L equal 10. That's going to be high enough for this discussion. You probably did something less than that, but you may have done an upsample factor of 10. You did something, all right, and we're going to talk about why you'll need to change whatever you did to land at Fs equals 80K. All right, there's a technical reason we're going to need that sampling rate. Okay, so in the video that we talked about, the video on sampling, the Matlab resample function, when we resample using Matlab to a lower sampling rate, okay, so let's say I change from 20K to 10K, that's lower. Well, you go back to this block diagram, L would be equal to 1, M would be equal to 2 if we're going from 10K to 20K to 10K. L would be 1, M would be 2, and the role of this low-pass filter would be to remove any potential aliasing. Okay, so that's built in to the resample function. You can't stop it. All right, you can't stop it from doing that filtering step unless you rewrote that code. All right, so it turns out that what we want to do for demodulation, we actually want the spectrum to fold back down, which is essentially aliasing, back down to baseband. All right, so when we talk about an anti-aliasing filter, the assumption is that we are doing everything at baseband. So we're doing something different with sampling. We're actually sampling to demodulate, so we actually want aliasing in that case, and so we can't have, that's the conclusion that we have, we can't use Matlab's resample function to change the sampling rate of the signal. Alright, so I can't just resample down to like 10K without it filtering out what I want to generate. Okay, so with that being said, let's get back to it. All right, so at this point, let's assume we have the AM DSB transmitted or suppressed carrier signal, and we know what that looks like. All right, let's sample the spectrum so that it replicates down to baseband. So if this was an analog signal, we could figure out which sampling rates would actually do that. All right, so that was essentially the point of that Matlab assignment where we were looking at the triangle shape and trying to move that back down to baseband. Okay, so the question would be, if this is the situation, what sampling rates will actually do the job? And what we need to find out which sampling rates will work, we need to satisfy two conditions. The first condition is that we have to sample at least fast enough to capture the baseband signal. All right, if you start sampling less than that, then you can't reconstruct the baseband signal because that will fold back down on itself and give you a distorted spectrum. Okay, so we know that the downsampled sampling rate that we would need to move this spectrum back down to baseband has to be greater than 8K. The other thing that we know is that when we take integer multiples of whatever sampling rate we choose, those integer multiples have to land back at 20K. All right, so that's in effect thinking about the problem backwards. What I want is the 20K to march back down to baseband, but think of it, it has to be true that if it marches back up, it would land at 20K. So any integer times FSD has to be 20K in order for the signal to show up at baseband. All right, so if I start taking integers, 1, 2, 3, and so forth, I can calculate possible, I forgot the subscripts, possible downsampling rates. Okay, so 1 is 20K divided by 1, which is 20K, 20K divided by 2, which is 10K, 20K divided by 3, now that's 6.67K. That violates our minimum sampling rate for baseband, so we know we can't do that. All right, so we need one of these two rates to downsample by in order to demodulate the signal. Okay, so let's go back to the original possibilities that would show up from your simulation. You chose one of these rates. Okay, what we're trying to do is downsample without an anti-aliasing filter, which means simply take every nth sample without the low-pass filter. All right, so the question is, which of these rates from our original simulation would be natural for converting down to 20K or 10K? All right, and so when I look at this list, only 80K is an integer multiple of one of the two downsampled rates. So 80K is, 20 times 4 is 80, 8 times 10 is 80. All right, so 80K is the only one that has an integer multiple of those two sampling rates. Okay, so what we can do is modify your original AM/DSB suppressed carrier simulation to upsample by a factor of 10 so that the speech signal that gets modulated, so upsample speech to 80K, multiply by the oscillator, we know that signal is sampled at 80 kilosamples per second. Okay, the spectrum is still showing up where we want it. It still looks like this. Okay, at 20K and minus 20K. When you do plot spec, that's where the spectrum shows up. Okay, so we've got it at 80K, and if I wanted to convert that, I would simply downsample by either 4. If I do 4, I would land at an FSD of 20K. And if I downsampled by 8, I would end up with an FSD of 10K. All right. So in Matlab, this is the code you need to add to your simulation. Okay, this is the downsampling process. So you start with a vector y, Okay, this vector y would be our modulated digital signal sampled at 80 kilosamples per second. You form a vector n. It's just 1 in steps of m all the way out to the length of y. So that would look like, 1, 5, if m is equal to 4, 9, 13, so forth. Okay? And then when I take y of n, I'm going to only return these samples. I'm going to discard samples 2, 3, and 4, okay? And I'm going to return that into yd. So yd is essentially downsampled by m. So I put yn, downsampled by m, I get yd. Okay? So if you look at the spectrum of that, your new sampling rate is now FSD. So you type plot spec yd 1 over FSD, and you should see what looks like the original spectrum. You can also listen to it, okay, by playing it back with the sound function. Okay, so I want you to do that for both downsample rates. Okay, so if you use m equal 4, you're essentially using FSD equal 20K. And when you do m equals 8, FSD is 10K. Both of these should work. All right, you might play around with this and write your code and modify, write your code as a function of m and play around with what happens when m is equal to 5. It's going to definitely move it down in the spectrum where the spectrum overlaps at baseband. It's going to sound pretty bad. Okay, so that's the assignment. It's not very hard, but the concept is what I'm after. I need you to pay attention, go through this, and understand how things are moving around and why I needed to upsample to 80K instead of one of these other rates. It's because I couldn't downsample by some integer number to move 20K down to baseband.